Okay, here's the idea. Here's the definition. An instruction called J is data dependent on some instruction I if, here we go, I produces a value that's needed by J.
See, this is what we needed for the last homework.
All right?
It was in the book.
Yes.
It was in the book.
Yeah.
Yeah,
It was in the book.
sometimes reading books, you know, there's a story in the Bible where the Ethiopian eunuch, you know, he gets confronted by Philip, and Philip says, do you know what you're reading? And the eunuch says, how can I except some man should show me? So Philip hops up in the chariot and explains Isaiah to the Ethiopian eunuch. So sometimes
But
it's nice to have a person explaining it.
Dr. Morris, I read the book after you had explained it, so it made perfect sense to me.
Yes, so if, right, and so when I took the first time I took the algorithms course, when I took it at USC, we used the CLR book, same one I use, and I would read this stuff, and I'd go, what is this guy talking about?
Yeah.
Okay, and then I'd either write the code or get someone to explain it to me, and when I finally figured it all out, I'd say, well, why didn't he say that? Then I'd go back and read the text, and I'd go,
Oh, he did.
I just didn't understand
And
what he said.
the book was very simple, so it was,
In some areas.
Sir,
In
that
some,
part I understood.
I also notice a problem when I read book. It's like I lose the reasoning power. It's like to be taken granted whatever you read.
Yes.
When we explain it, you get a reasoning. Why is it this
Yes,
way?
correct. Yeah, all the peripherals not there. That's right.
Yeah.
And you don't have the opportunity to say.
Trying to figure out what it was.
And have you ever played? Are you familiar with a game called charades? There's an American game called charades where you try to work out like the name of a textbook, but you can't talk. Okay, so you make motions, right? So sometimes you'll play charades, and the guy will go like, you know, and no
What
one's
do you
getting
mean?
it, and he
Yeah.
thinks by doing this 1,000 times that
The-
people are going to get it. Here's an idea: if this doesn't work, hey, try something different. Okay, so that's what classroom instruction. That's where classroom instruction gives you the benefit, because if what the book says or what I'm saying, if you're not grokking what I'm saying, then I can try saying it a different way. Okay, so by the way, instruction J is data dependent on instruction K, and instruction K is data dependent on instruction I. That's called a transitive dependency chain. All right. So this
It's like
is
a circle?
no, it doesn't have. No, it's not a circle. It's here's an example. Load into R1. A offset by R0, and then dad into R3, R1, R2, and then dad into R4, R3, R5. Okay? It's not obvious that this instruction
It's
is dependent upon that instruction,
yeah.
but it is transitively, because this instruction is dependent upon that because of the R1.
Right.
Okay.
And
This
that,
instruction is dependent on this one
Because
of
the R3.
So that's called a transitive dependency chain.
So basically you can look at that when Saul thought about Saul.
Well, in this case, it also happens to have a stall. It doesn't have to have a stall.
Yeah.
In this case, it does.
Okay.
There's still the dependence is still there.
It's like you indirectly affected.
Yes, yes, and that's called a transitive dependency chain. By the way, that's where you get into issues, because these can be quite long and not at all obvious, all right? And by the way, they can be very hard to detect if the values flow through memory, okay? So I create something and I store it in memory, and then later I pull it in memory, so now it's got a completely different name, okay? Right? Right? Very hard to detect. It can be, okay? And I mean, if I'm looking at a window of 100 instructions, right? And the hardware superscalar schedule is saying, well, I can do this one, this one, this one, and this one. Well, the one that's way down here might be using a register that was obtained by loading up a memory slot here that some guy way up here produced. Different name, nothing's the same. And they're very hard to find. Okay? They can't be very hard. Now here's the classic example we've seen. Alright? Here we go. The data is data dependent on the load, and the store is data dependent on the DAD, and it's transitively data dependent on the load. Alright? Why?
Because R2 is effective in DAD, and R3 is effective in the store in the double.
Did I do that right? Oh. Yes. Same example that I gave here, I think. Yes. Yes. All right. Good. Now, here's the deal. All right. Instructions with true data dependence. This is an important issue to make. Okay. They cannot be completely overlapped without stalls, and they cannot be reordered. In effect, instruction I must execute before instruction J. All right?
Basically, you mean it can't be solved if they are true
No,
data.
I'm not saying it can't be stalled.
I mean solved.
Excuse me, solved. I'm saying that you can't do them completely in parallel unless you figure out a way to do it. There's no way that the DAD instruction can ever go before the load.
Right.
Period. End of story. You can't. All right? You can't. All right?
How about store after the load?
And similarly, the store can't proceed until the DAD. So they have to be done in this order, and they couldn't all three go at the same time. Okay? All right? So, now, so let me back up. So just to make sure that we're understanding the context is a true data dependence. A true data dependence. In other words, it's not the name R2 that's important here.
It's the
what's
value
stored in R2 that's important. Right? A true data dependence, I could make this R7, R7. Okay, R12, R12. Doesn't matter what it's called, it's the content, the true data that's relevant. Okay? And when there's a true data dependence, okay, these conditions hold. I want to contrast this with a name dependence. All right? Here, okay, instructions use the same name, but there's no flow of data between them. All right? And again, two flavors in the text. There's what's called an anti-dependence and an output dependence. All right? Here's the idea. An anti-dependence is, by the way, I comes before J. All right? And an anti-dependence is when J writes a location that I reads.
right after read.
Here. All right? All right? This is an anti-dependence. All right? J, let's try it again. J writes to a location, in this case R3, all right, that I reads. Right? I can't reorder it. You see it? I can't reorder it. Okay? Now, all right, so I'll get to the other. And the second was an output dependence, where J writes to a location that I writes. Okay, so here, J writes to a location that I writes to. Do you see if I swap the order, it would change the outcome?
Yeah, right after right.
You can't reorder this, you can't reorder that. Okay? But there's no flow of data. Okay? So by using a different name, I can resolve it. Look. You see these are the same?
Mm-hmm.
Okay? I just, instead of putting it into R3, instead of using R3 as the base register, I use R. Now obviously, the code above would have had to have produced, instead of R3, it would have had to have produced R9.
But do it have to be the same value?
It has to have the same value.
Just a different name.
Yeah, different name. And by the way, now doing this, you see I can put them in any order that I want.
Right.
So name dependences, okay, are not true data dependences. and they can be easily resolved just by using a different name. Okay? All right, and here's the example with the output dependence, right? It's now solved, and I can do these in any order. All right? All right, so, continuing. Once again, assume I precedes J, and the three flavors of hazards. There's a read after write, so-called raw.
Right
There's a
after
write
write.
after write.
And right after read.
And a write after read.
And read after read.
There's no such thing.
It's
A read
not?
after read's not a hazard. Sure, I can read after read, and it's not a hazard.
Because it won't produce anything.
Doesn't matter. Read after read, okay. So, read after write. J tries to read something before J writes it. Okay? All right? Let's make sure we understand what it's saying. The classic example is a load hazard. And if you look in WinMIPS, a load hazard, it'll say raw.
Mm-hmm.
In WinMIPS, you had a load hazard. So, load double into R1, A of R0, and then dad. Last. Dad into R4, R2, R1. All right? Good. So, fetch, decode, execute, memory, write back, then fetch, decode, raw, and write back. All right? That's called a read after write. A read after the write. Or you're reading it after the write. Do you see that? All right? And that's called, it becomes a hazard if J tries to read it before I writes. If this X were here, yes, what would the dad be trying to read?
R1.
And it would be wrong, because it's trying to read it before I writes it. Is it clear?
Yes.
No?
Yes.
Suppose that I did this. What would be the problem?
It would have the value of R1 before it actually executes the instruction.
It would be R1 wouldn't have the correct value in it. So it's reading R1 before R1 is written to.
Yeah.
Okay?
Yeah.
And so this is called a raw hazard. So in WinMIPS, raw. And
Shouldn't it be read before write?
no. The hazard is read after write. Okay? That's the kind of a hazard.
But is this reading it before the load writing it?
Before it writes the correct information. It's
Yeah.
reading the wrong information.
This is what's supposed to happen. You're supposed to read
After
after
write.
write.
Oh,
Okay?
okay.
When you don't do that, it's a hazard.
Oh, that's the same thing as right before read.
Well,
No.
maybe. So, sure. In Shanika's computer architecture book, you can call it a WBR, right?
Okay,
before
is it not the same?
It is the same thing. It is the same thing.
Because I don't say daddy is try to read it before it is written. That's what I'm thinking.
Right? And so, here's a write after write. Now, we're not going to be able to understand this one, and I can't give you an example because this can't happen in the processors that we've looked at so far. The idea is J tries to write before I writes it. All right? So the write is out of order, right? If I'm supposed to write.
Scoreboard said that was one of the main hazards
I'm
that.
supposed to write a value here, all right? Then you come along and write to there, okay?
Mm-hmm.
Now, when everything's said and done, what should be there?
That one.
That value, right? Well, suppose that you came along and through some set of circumstances, you wrote first, and then I come along and I write. Now what's happened?
The wrong values
The
in
wrong
it.
value's in there.
W-A-W.
Right after right. Yes, so it's done in the wrong order, okay? And it leaves the wrong value. And again, this can only happen in out-of-order execution processors, which we have not yet considered, all right? And by the way, it can also happen in processors that have variable length pipeline stages, and we haven't looked at those yet, all right? And then the last one is a write after read, okay? This is J tries to write before I reads it, all right? J tries to write, and again, only out of order. So here's the idea, all right? Suppose that he wants to read what's there, all right? So Hyder wants to read that value. Remember, it's a write after the read, okay? So you're supposed to read it first. So you take that, then I come along and write. Now everything's cool. But what if this happened? What if, before you had the chance to read this,
You already wrote.
I wrote something there? Then what are you going to get?
The wrong value.
Wrong stuff.
Yeah.
Okay? All right, so that's the third kind of a hazard, which is a write after read, where J tries to write before I read it. And again, this one can only happen in out-of-order execution processors, which we have not yet looked at. And again, RIR is not really a hazard. Let's see if we can go on. This is almost silly, but watch. So H and K are not control dependent, okay? Whereas I is dependent upon predicate P, J is control dependent on Q. By the way, J is not dependent on P. So
Right.
This idea of control dependence, okay, it should be obvious. If there's a control dependency on a branch, it can't be moved outside the branch, okay? And if there's an instruction that's not control dependent, it can't be put inside, right? It kind of makes sense. So when you're rescheduling instructions, you can't take stuff out of a loop body, okay, and put it somewhere else, nor can you take something that wasn't in the loop, let's
And
say,
put it
And put it in the loop.
Well, it doesn't have to be just a loop, but that's the example that most people can click with. So that's control dependencies. All right? Good. So now, I didn't give you an explicit homework, I don't think. Let me see if I did. I don't think I did. Yeah. As I recall in this class, I did. Okay. So here's your homework. All right? Read A8 carefully. Appendix A8. Read section 3.2 carefully, and read section 3.3 carefully. Okay? This is